don't care about the order.
Okay, so what we're going to do now is I guess this is lecture 29 of problem solving, and we were talking about a Putnam problem from 2005 on question involving sums. And so what I wanted to do is I want to just comment a little bit about, if we were, not clever enough to notice, some of the items, especially in the last case, is there a nice way to at least get a reasonable number of cases to check, brute force by hand? Coach Schwartz, I mean, I think that was really important. So this is 2005 B2. And so the problem is we have K1 plus Kn was 5n minus 4. 5n minus 4. And we want 1 over K1 plus 1 over Kn equals 1. So we talked about using Cauchy-Schwarz and finding pairs. And so now let's assume we have K1, K2, K3, K4. If K1 is less than or equal to K2, and so on, if K1 equals 1 equals 4, only option is 4, 4, 4, 4, which works. So now we have, case 1, K1 equals 2, case 2, K1 equals 3. And we just need to show that there's nothing in that case. So in this case, we would have the triple K2, K3, K4, such that K2 plus K3 plus K4 equals 14. How many ways are there? How many triples are there to check? Two of you in this class should know the answer. You've done research with me related to the answer to this problem. It's 14 plus 3 minus 1, choose 3 minus 1. And here we want K1 plus K2 plus K3 to equal 13. The answer is going to be 13 plus 3 minus 1, choose 3 minus 1. So I call this the cookie problem. You might know this as the stars and bars problem. It might actually be a little bit different because in what I'm doing here, I'm considering the order matters. So imagine you have C cookies and P people. The cookies are identical. The people are distinct. So this is not like engineering graduate school where the professor can tell the difference between the different graduate students. Everyone can be distinguished. And I want to know how many ways can I assign cookies to people? I don't care which cookies you get, I just care how many. So we have x1 plus x2 plus x3 equals C. I'm dividing the cookies among my people. And in general, if it's not just 3 people, if it's in general P people, you would just write it as plus dot 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 plus XP. Each XI is a non-negative integer. And the solution is imagine C plus P minus 1 cookies. Choose P minus 1 to eat. It gives P minus 1 partition points. So for example, let's say we have C equals 8 and P equals 3. So 1, 2, 3, 4, 5, 6, 7, 8 cookies, and I have to add 2 more. Let's do P equals 5. So I have to add 4 more cookies. And now imagine I eat P minus 1 cookies. This is going to be x1. It'll be 3. This will be x2. It'll be 3. This will be x3. It's not their day. They get no cookies. This will be x4 equals 1. This will be x5 equals 1. By putting in 4 partition points, I'm now left with C cookies. Everything up to the first Eden cookie goes to the first person. Everything between the first Eden and the second Eden goes to the second person, and so on and so on and so on. There's a one-to-one correspondence between the number of ways I can choose 4 cookies from 8 plus 5 minus 1 and the number of ways to divide the cookies. Okay. And that's where you get the formula C plus P minus 1 choose P minus 1. Now, 33011 is considered different than 11033. Okay, so this overcounts in terms of what we want for our problem. All right, but worst case, in terms of just getting a sense of just how bad would the computation be? We would have 14 plus 3 minus 1 choose 3 minus 1. All right, so that's 14, 15, 16, choose 2. All right, 16 choose 2 is roughly 16 squared over 2. 16 squared is that 256? So 128. All right, it's not pleasant, but as an upper bound for the number of cases to check, it's not horrible. And again, that's not using any of the symmetry. So if we just start going through the problem, let's say the first one is 2. We can't do 2, 2, 2, 3. So if we do 2, 3, there's not going to be that many cases. This is an upper bound on how many things to check. Right. The next one is going to be a little bit worse. No. The next one's going to be smaller. So it's even going to be better. Okay. So you can do the problem without too much trouble by brute force. So if you were not clever enough to notice the Cauchy-Schwarz, when is it an inequality, which was really nice. If you just went through a full brute force case analysis, upper bound is around 120 things to check, maybe double 240, but you'll see that there'll be far less in practice. So as a nice exercise, we just showed that the number of ways to divide C cookies among P people is C plus P minus 1 choose P minus 1. What if we don't have to give all C cookies away? So if every cookie has to be distributed, it's C plus P minus 1. If I don't have to give out every cookie, it would be the sum of little c goes from 0 to big C of C plus P minus 1 choose P minus 1. And actually, let me just make it clear that this is a little c. So does everyone agree that this is the number of ways to divide up to big C cookies among P people? So this is a binomial sum where both the top and the bottom are changing. Does anybody know how to evaluate this binomial sum?
What if you just add one more person in?
Yes. It's just C plus P plus 1 minus 1, choose P plus 1 minus 1. Extra person gets the leftover cookies. And this is, combinatorial reasoning at its finest. Tell a story. If I'm dividing up cookies and there are some cookies that aren't distributed, well, just imagine there's an extra person who gets the cookies. We'll name them the professor, right? And out of the kindness of their heart, the professor will take the extra cookies. If the professor is unavailable, who would step up? No, well, I mean, I'm sure you would, but which classic character from television history? Cookie Monster, right? Cookie Monster would always step up and take the extra cookies. There was a beautiful clip years ago when the Cookie Monster first met the Count, and it was your irresistible force versus immovable object. Cookie Monster wanted to eat the cookies, the Count wanted to count them. they compromised and they counted the cookies as they were eaten. How many was restored? But I love this problem. This is one of my favorite problems of all time because it shows you the power of looking at things the right way. If you try to handle this as a binomial sum, it's hell. But if you view it as, I just have an extra person who takes the leftover cookies, it's not so bad. All right, any other comments on this problem? This is a really nice problem. A lot of good math behind it. Cauchy-Schwarz inequality is really worth seeing. The difficulty frequently is figuring out how to apply it. All right, so I'm going to pause the recording now. Okay, so we just talked about the following problem about trying to find the choices of S and T that maximize the ratio of the area of the two rectangles to the area of the whole triangle. And one of the things that was done was to say, well, we can do an affine transformation, and without loss of generality, we can assume some shape about the initial triangle. Let's see. So if we draw the line like this, one of the things that you notice is if I expand things out like this, what can you tell me about the change in lengths of all these sides? So we have CP, CTC, corresponding parts of congruent triangles are congruent. So if I change the angle at the top and sweep things out, does that just rescale all the lengths by the same amount? And so the ratios are not going to change. And so without loss of generality, I can do this on both sides, however I want, and it's not going to change the relative. So I can assume that it's the triangle structured as you want, or without loss of generality, it's enough to just do 1/2. And if I want to just look at a triangle, say an isosceles right triangle, without loss of generality, it would be enough to look at an isosceles right triangle as well. There's lots of different. No, not right, 45, 45. Right would be on a sphere, exactly. Sorry. So, again, this is the idea you want to have in mind. Can I make some simplifications to the problem to make the algebra simpler? And my idea was, well, by swinging the angle at the top, I'm not changing the relative ratios. So if I wanted to, I could look at an equilateral triangle. I could look at an isosceles right triangle.
Right. Yeah. Actually, your solution is correct. My solution is correct because after the information, these things no longer have to be have right angles.
Correct. So you've just got to be very careful when you're doing things. And so the idea of adjusting the triangle and saying that without loss, you want to prove if you're using an affine transformation that it really is preserving the ratio of the areas. And you're doing this. How many of you remember the phrase CP, CTC? Corresponding parts of congruent triangles are congruent. This should be from your old geometry days. And so because of that, I know that I'm not going to be changing any of the ratios. And so then it comes down to, well, what's the best way to do it? It's sometimes not bad to try to build some intuition. What would be an easier problem to do? So this is the problem they asked. What might you do instead of this problem? One rectangle, right? So do something simpler. And so, I'm not sure what the best way is to draw things. I'll draw it like this. So this is the point 0, 0, 1, 0, 0, 1. I now have, and this is going to be really nice because I've got an isosceles right triangle. So this is x, this is x. So the area of my rectangle R is just x squared. The area of T is just 1/2. It's x times. Yeah, it's not x squared. This is the line y equals 1 minus x, right? the slope is negative, so I know it's got to be something like y is negative x. When x equals 0, y equals 1. So this here would be 1 minus x. So the area would be x times 1 minus x. And you need to maximize x times 1 minus x. Where do you max it? How is x1 minus x maximized? Midpoint. And so if we plot A of r, this is just a parabola. Here's 0, here's 1, here's 1/2. We could also expand it out as x minus x squared and do calculus here. I'd rather avoid the product rule if I can. And so we see that here, the answer is 1/2. Here, the answer is 1/3. What do you think the more general question might be? I'm sorry? Yeah, if you have n rectangles, what would you guess? I would guess 1 over n.
Or n plus 1.
1 over n plus 1, yeah. Right. Depending on how you're defining n. But since you said n rectangles, it would have to be n plus 1. Yes. So I would guess that would be a nice generalization of this problem. But again, when you're trying to get a sense of what the answer might be, sometimes if you do an easier problem, that might give you a sense, okay, with one rectangle, I went halfway up. What might I do? Now, of course, what you would love to do is maximize the first one and then maximize the next one. Can you do it that way? So first, choose your first rectangle R to take up as much area as you can. And then when you're done with that, choose S to take as much as you can from what's left over. Do you think that's going to give you this? No, because if we choose the first rectangle to maximize what we can get, that's going to give us 1/2. And then if we did the next one, we would get 1/2 of what was left over there. So we would have 1/2 and 1/4 rather than 1/3 and 1/3. Right? So does everyone see that we could try to do it as two different maximization problems and say, first, I'm going to choose the R that gives me the greatest possible area. And then I look at what's left over and I choose S to give me the greatest possible area. That doesn't work. There is a way to avoid using multivariable calculus for this problem. Yes.
I have a different solution that I think doesn't use as much calculus.
Okay, let me quickly say my solution and then I will switch to you. So here's what we could do. So without loss of generality, we've said we might as well assume that we have an isosceles right triangle. So y equals 1 minus x. So let's choose some point x for the first rectangle R. So this is going to be x, this is going to be 1 minus x. So we fix x, and now we choose some new point. Let's call that u. So 0 less than equal to u less than equal to x. And if this is u, what's this distance over here? One minus x minus u. Well, let's see. The whole thing is 1 minus u if we go all the way down. But we're subtracting 1 minus x. So is it just x minus u? I get x minus u, is that correct? So we're viewing this as, so this is 1 minus u minus 1 minus x. So here's R, here's S. So the area of S is equal to x minus u times u, right? And so for given x, what u is best? For given x, best u is from x minus u times u prime equals 0, right? So that's going to just be xu minus u squared prime equals 0. So that's going to become we're taking the derivative with respect to what? U. So it would just be, derivative with respect to u would be just x minus 2u equals 0. Therefore, u is equal to x halves. Okay, and so now area of R plus area of S. So when u equals x halves, what's the area of R? It's going to be just 1 minus x times x. And then we added the area of S, which is x minus u times u. So if u is x halves, x minus u is just going to be, I think, x halves times x halves. Am I doing this right? So we would then get x minus x squared plus x squared over 4. So maybe x minus 3/4 x squared. Yes. So derivative equals 0 implies 1 minus 3/2 x equals 0, which implies x equals 2/3. And there's the answer. So rather than doing it as a multi-variable problem with both A and B, what I did is I did it as a series of one variable optimization problems. First, fix an arbitrary x, and then say for that rectangle, what's the best we can do with what remains? Then we vary x. And as long as we do it like that, that's very different than saying, I'm first going to optimize where I put the x and then optimize what comes afterwards. So it's a slight difference in terms of how we do it, but this is a way to bypass multivariable calculus. Is it worth bypassing multivariable calculus? Why? This is where it becomes debatable. I can do this more easily in a pre-calculus class. I could also use this as motivation for why we want to learn multivariable calculus, so that rather than doing it as two separate optimization problems, we can just do it as one. I think there's advantages and disadvantages to both ways. There's not, this is not, what is my favorite college football team other than NESCAC schools? No, try again. The Ohio State, right? Right? It's not like this is the proof. This is a proof. There's more than one ways to prove things. The whole point of the problem-solving class is to just talk about different perspectives so that you have a bag of tricks and you can try different things. Okay, so I will turn it over. Somebody said they had another way to do this?
Yeah.
All right, so I'm going to stop recording.